Okay, so welcome back everyone for the third day of this wonderful conference. And the first title of the morning is Eran Palti, who is going to tell us about the distance conjecture and potentials.
Okay, thank you. Good morning, everybody. And let me first of all thank the organizers for the opportunity to speak and for all the hard work running this really enjoyable conference. So the title of my talk is Distance Conjecture and Potentials, and it will be mostly based on recent work with Dieter Lust and Kumun Rafa. So string theory is a framework where the vacuum energy is calculable, and that's, of course, a very interesting thing. And in particular, because it allows us to study relations between the vacuum energy and other properties of the vacuum. So when I say vacuum energy, I mean the minimum of the potential. So the value of the minimum potential could be related to other properties of the vacuum, and string theory allows us to see if that's true. And guided by simple vacua, the idea of this talk and the work related to it is to attempt to relate properties of the vacuum energy to some more general microscopic or principles ideas of string theory or quantum gravity, or in other words, try to understand if there are Swampland constraints that relate to the value of the vacuum energy, so to the minimum of the potential. And I think it's a difficult problem, a difficult topic to think about, and that means that there's typically no proofs of many of the statements that I'll try to make. But I think, nonetheless, it's a worthwhile endeavor to think about it, and perhaps we can learn some interesting things along the way. So the relation that I'll be interested in for this talk is the following question. Could it be that there is an infinite tower of states whose mass scale, so the mass scale that controls the infinite tower of states, is related to the magnitude of the cosmological constant? So by which I mean the minimum of the potential. So could it be that whenever the cosmological constant, the vacuum, whenever the magnitude of the cosmological constant goes to 0, there is an infinite tower of states whose mass scale goes to 0. Could there be such a relation? And, of course, there are many correlations between these two quantities, a correlation between the magnitude of the cosmological constant and the infinite tower of states. One famous correlation is if you take the internal space of string theory, the volume of the internal space to go to infinity, then any energy sources go to 0 in this decompactification limit, and that means that the cosmological constant goes to 0, but also an infinite tower of states becomes light. These are the Kaluza-Klein modes of the extra dimensions. So there are certainly many situations where there is a correlation between these two things, but of course we know correlation does not imply causation, and so one wants to ask whether there are more general arguments relating these two things. So I've introduced here an infinite tower of states with some mass scale, and there is another, this tower of states appears many times in the Swampland, and in particular it appears in the so-called distance conjecture. And the distance conjecture says the following thing: if you take a bunch of scalar fields, let's say with no potential, that have the following kinetic term, then you can use these kinetic terms to define a metric on the field space of the scalar fields. And then, using that metric, you can define a distance along some path in that field space, where tau is some parameter along the path in field space. And then, once you extracted this distance, there is the following conjecture that if this distance is much bigger than 1 in Planck units, I'll always work in Planck units, then there should be an infinite tower of states. This is where this infinite tower of states appears in this setting, with a mass scale m that behaves such that relative to the starting point, the endpoint mass is exponentially smaller. where alpha is some positive order 1 constant. And there's a possibility that this may also apply to fields with potentials. I think the most subtle application of this idea is to axions, where I think there is still some evidence that it actually holds for them, although there is some debate whether that's true or not. And, but this will not be so important for this talk because we will not really be thinking about axions anyway. So this is the distance conjecture. And here we get an infinite tower state, and the question is, can we think of some general reason relating this infinite tower state to the magnitude of the cosmological constant? So in de Sitter space, there's, I think, a very a simple and interesting way to try and understand why it could be that there's an infinite tower of massless states when the cosmological goes to 0, and that's because de Sitter space has an entropy associated to it, which goes like the inverse of the cosmological constant. And like in any other case that we know in physics, where there's an entropy, it should be associated to some microstates of the system, so log of the dimension of the Hilbert space. And therefore, you must get a lot of microstates when the cosmological goes to 0 for de Sitter space. And it's known that if you consider a single field inside the horizon of a de Sitter, then the entropy of a single field only goes like lambda to the -3/4. So that's not enough to account for this entropy. And you see that as lambda goes to 0, it gets nowhere near enough. And so it's natural to suggest that accounting for this entropy, you would actually need an infinite number of light fields as lambda goes to 0. In fact, this identification of the entropy of the de Sitter space with potentially an infinite tower of states that becomes light was indeed a tool that was used connecting this distance conjecture to these ideas of entropy in de Sitter space, because the distance conjecture indeed gives us this infinite tower of states. So if you identify the entropy of the de Sitter space with the entropy of the infinite tower of states of the distance conjecture, then you recover what's called the refined de Sitter conjecture, which puts this lower bound on the gradient of the potential. And the way to see that is if the entropy, which is the vacuum energy, which is the value of the potential, is given by the tower of states of the distance conjecture, then as you go further in field space, you get more and more light states, so the entropy has to keep increasing monotonically. And therefore, there has to be, the derivative has to behave monotonically, and the exponential behavior of the tower of states then translates to the fact that it's proportional to the potential. So this was the argument we presented in this paper. But of course, this whole discussion relies on this notion of entropy, and that is only true if you are in a potential where the minimal eigenvalue is not too negative. So it should not be more negative than the potential itself. If that's true, so if this is satisfied, so if it's more negative than the potential, there is no notion of entropy, and therefore this argument shouldn't work. So this is what led to this refined conjecture. But this is one interesting notion, I think, where we can see that perhaps indeed accounting for de Sitter space entropy, you expect an infinite tower of light states as lambda goes to 0. So let me give another example, which is kind of related to other Swampland conjectures. Let's think of type 2b in a Calabi-Yau manifold and turn on Ramon-Ramon fluxes. Then these Ramon-Ramon fluxes will induce a potential. And the value, the form of this potential is intrinsically related to the behavior of the gauge couplings of gauge fields in this compactification. So you can see that very easily in the following sense. There are gauge fields coming from the Ramon-Ramon 4 forms, expanded in 3 forms. And in the same 3 forms, if you expand the 6th form, then you also get 3 forms in the external space-time. And you can write the potential that's induced by fluxes, these QAs are the fluxes, in this very nice way, following this very nice work over the past few years. You can write it in terms of Minkowski 4 forms, so that's the field strength of these 3 forms, plus some coupling to the fluxes. And then if you integrate out these non-dynamical 3 forms, you get back the scalar potential. That's the flux, Ramon-Ramon flux-induced scalar potential. But you see, these 3 forms kinetic terms are exactly the same, because they come from this internal 3 forms, the same as the gauge field kinetic terms. So in other words, this kinetic matrix here is nothing but the gauge kinetic matrix of that model. And similarly, the value of the potential is actually nothing but the gauge force between two charged particles, between the charged particle and itself. So if you take a particle of charge QA, this is nothing but the magnitude of the gauge force, the repulsive force. And now, the weak gravity conjecture tells us something about the repulsive forces. It says that you cannot have a charged particle and send the repulsive cell force of that particle to 0 without having something go wrong in your theory. You cannot do that unless you get an infinite tower of light states if you do that. So in this case, because of this relation, that's precisely the statement that you cannot send V to 0 without having an infinite tower of states go to 0. So this is true for pure Ramond fluxes. If you turn on more fluxes, the relation is not so simple. Nonetheless, it was shown in this work that any kind of fluxes you turn on, you can always write the potential in this way in terms of free forms. And so one might wonder whether some statement like this has some kind of weak gravity force interpretation in terms of the object that couples to these free forms, which are d minus 2 branes. And I should comment that it may even be that the relation between the tower state and the potential could be causal, in the sense that it could be that potentials could be emergent from integrating out these light, I say domain walls, but they're really just localized membranes. So you just think of a membrane and integrate it out, you will generate these kinetic terms, and then that is exactly related to the potential. But I will not discuss this anymore. So those are two arguments which are a little bit indirect, and the first one only applies to the sitter space. And what we were interested in our work is to think, can we associate an infinite distance to this lambda goes to 0 directly? Again, we're inspired by the distance conjecture that at infinite distances you get infinite tower of light states. And if there is a correlation between lambda goes to 0 and an infinite tower of light states, it could be that because this really has some kind of infinite distance interpretation. Could that be true? And we try to argue that yes, that's true in the following sense. If we think about this distance conjecture that I discussed in the first slide, let's think these scalar fields are, let's say, moduli of Calabi-Yau manifolds, the moduli of the Calabi-Yau, then in fact you can just rewrite this in a different way. You can rewrite it as the integral of the whole of space-time divided by the volume of space-time of this variation of the Calabi-Yau metric. Or this could also be the full space-time metric, and you just vary the internal components of it. So in other words, the moduli fields, what are they? They are just changes in the metric of the Calabi-Yau. So the distance conjecture is a statement about distances in metric spaces. That's what the distance conjecture is really capturing. It's capturing a distance associated to variations of the metric. And in fact, this suggests that the distance conjecture is not necessarily just a statement about scalar fields, but a statement about any kind of field variations. So, and indeed, if you have any kind of field that has a kinetic term, then that field will have an induced metric on its field space, which is just what you contract the kinetic term with to obtain a term in the Lagrangian. So any field will always have a metric on its field space. In the case of the metric variations, this metric on the field space is just these two factors here. And once you have a metric on a field space, you can associate a distance to it. And then what we propose is that the following, take your space-time to be a product of some external homogeneous space. So that means like de Sitter or anti-de Sitter or Minkowski times some internal space. Then in the Einstein frame of this external space, it must be an infinite tower of states that become exponentially light in the distance variation of any kind of field, where the distance is defined in this way. So this is a kind of slight generalization of distance conjecture, inspired by the fact that really the distance conjecture is telling you about variations of the metric. That's what it's capturing. It's telling you that you cannot have infinite variations in metric space without getting the problems, getting an infinite tower of light states. So that's the idea. And now there's one thing that's subtle. This formula actually is not completely general. It's only true for so-called transverse traceless metric variations. If you vary the volume of the space, then you have to do a bit more work because of this Einstein frame condition. But it's easy to show that, let's say, if you do a Wahl rescaling of the internal space, then the kinetic term for this field is linear, the canonically normalized field is some order 1 factor times this tau, which appears in the exponential of the Wahl variation. Or in other words, the distance in metric space of Wahl rescaling goes as tau. where tau is the thing in the exponent. And this is all we're actually going to need for the next part, because now the idea is very simple. Let's think about ADS space in global coordinates. Then the metric takes this form, and you see it has this Weil factor out in front, and this Weil factor is precisely related to the magnitude of the cosmological constant. This means that we can consider the distance in the external metric space upon variations of the cosmological constant. So if you change the cosmological constant, you're changing the metric of the external space. Now this is a little bit different to changing the metric of the internal space, but at a fundamental level, string theory shouldn't distinguish between the metric of the external and internal space. They're on the same footing, they're on equal footing in string theory. So if there's a distance conjecture for the internal metric, it's natural to associate a distance also to the external metric variations. And what is that distance? Well, we can see that lambda goes to 0 if tau goes to infinity, so it's an actually infinite distance. And further, as we showed for the internal volume case, the distance is some order 1 factor times tau. So tau is the canonically normalized field for measuring the distance, and tau is log of the cosmological constant, and so the distance is measured as log of the cosmological constant. Then if we apply the distance conjecture, which says it's exponential in the distance, we get that it must be power law in the cosmological constant. In other words, the statement is really very simple. If you take ADS space and you go to the flat space limit, so you send lambda to 0, then you are traversing an infinite distance in metric space of the external manifold. And the distance is a power law in lambda. That's basically the statement. Now I should say, a word of caution, we're not completely sure how to implement the Einstein frame condition for the external metric variations, which basically means that we're not really sure about what this order 1 factor is, but we are quite sure, we are very sure, I think, that the canonical measure of the distance must be tau. So it must be exponential, so it must be log of lambda, which gives you this power law. I should say something perhaps important here. The distance conjecture is not necessarily related to how much energy you put into your variation. So of course, imagine you're lambda very, very small, and then you say, well, it costs me hardly any energy to move this to Minkowski or to the Stitter. I just need to add a little tiny bit of energy, and then how much harm can this tiny bit of energy do? But the distance conjecture is precisely telling you that this energy, the amount of energy you add, is not really the thing that sets the tower of light states. Because, for example, moduli spaces cost you no energy to go as far as you want. So what it's telling you is that the important things are not necessarily how much energy you put into the system, but how far you move in field space. And so even if you're very, very close to the flat space limit, still you're at infinite distance away from the flat space limit. So this is the point we wanted to make. So these ideas led us to the following conjectures. The so-called ADS distance conjecture says that imagine you have ADS-D space in quantum gravity. Then there's an infinite tower of states whose mass scale as lambda goes to 0 behaves as lambda to the power of alpha, where alpha is some positive order 1 constant. And in fact, this is true in any string theory solutions that I know of that is an understood 10 or 11 dimensional solution, so something that we are confident really does come from string theory, we are sure about it. And there's something special in all the solutions. It's not just an order 1 constant, but it's in fact precisely 1/2. And the strong ADS distance conjecture says the following, says that for supersymmetric vacua, and I will also try to explain even maybe for non-supersymmetric ones, in fact alpha should be 1/2. So for supersymmetric vacuum, alpha is exactly 1/2. And alpha is 1/2 is a very special value because lambda to the 1/2 is precisely the radius of the ADS space. What that means is that the radius of the ADS space is at the same mass scale as the infinite tower of states. And if you think of this infinite tower of states, let's say it's Kaluza-Klein mode, it tells you that the radius of the internal space and the external space are not parametrically separated. So this is what's called no separation of scales. So this no separation of scales could be related to a different Swampland conjecture, to an obstruction to an unbounded number of space-time filling massless matter. So this was conjectured to be the case. In other words, you cannot have an arbitrarily large, parametrically large number of massless fields that fill the whole of the space-time. we know this very familiar from like Minkowski space. The rank of the gauge group, for example, is always bounded. I mean, it can get huge, but it cannot be parametrically large. It's always bounded. And we know that that's also related to things like tadpoles. And if you geometrize the manifold, like go to F theory, then it's related to the compactness of the internal space, which is indeed precisely the condition that gravity is finite. So the Planck scale is finite. So this is a very gravitational condition. However, this is no longer true in ADS space. So for example, you take M theory and ADS 7 times S4 over ZK. This gives you an SUK times SUK gauge group, and you can make K as large as you want. So you can have parametrically large gauge groups in ADS space, something you cannot do in Minkowski space. So it's really qualitatively different. And this is against this conjecture that you cannot have parametrically large massless matter, but on the other hand, it actually does satisfy it in the following sense. This manifold actually doesn't have separation of scales, so the radius of ADS 7 is the same as the S4, and therefore there's no sense in which this is really an ADS 7 space. You cannot call this ADS 7 because you cannot make this space smaller than this one. And therefore, the massless matter is not actually space-time filling. It's a localized defect in the space-time. There's no sense in which it can be space-time filling, and there's no argument against arbitrarily large localized defect gauge groups. Of course, like ADS 5 times S5, the D3 branes can be made very large. There are defects in the space-time. So, in fact, this is fine with this conjecture as long as you cannot separate these two spaces. And this, therefore, naturally suggests that in quantum gravity, you should not have pure ADS spaces, but you must have ADS times some internal space of the same radius. And then when you go to the flat space limit, you go to Minkowski space of a higher dimension. And that's, in fact, precisely what this strong conjecture is capturing, that there is no separation of scales. In other words, there's no such thing as ADS-D space in quantum gravity, only spaces with an ADS-D factor. So this power of alpha is very interesting. And there are some arguments to suggest that in general ADS, not just supersymmetric, alpha is actually bounded by a half and below. So it's a half or bigger, and a half is precisely the bound for supersymmetry. And this argument is related to the refined de Sitter conjecture in the following sense. These kind of bounds typically actually come quadratically in string theory. So it's very natural in the Swampland. So it's very natural to suggest that perhaps the bound is actually quadratic here. And if that's true, then you see that if you have a minimum in ADS space, then it violates this. And if that's true, you must therefore satisfy the second condition. And because ADS space has negative V, this is actually telling you nothing but the statement that the mass of the lighter state is bounded from above by lambda to the half. And this was noticed already here after our paper came out on the de Sitter conjecture. And now, if we think about situations where you get bounds on masses like this in the Swampland, then typically these bounds are satisfied not just by one state, but a whole tower of states, an infinite tower of states. For example, the weak gravity conjecture, that's true, it bounds the mass, and we expect that at GM Planck we get a whole tower of states. It's also true for the scalar weak gravity conjecture, which is very similar to this. It says that the derivative of the mass of the state should be bounded, should follow this inequality, and then at large phi, this tells you that m must go exponentially, and that's precisely the distance conjecture. And the distance conjecture tells you this m is not just one particle, but in fact a whole tower of particles. So in other words, the ADS, this condition of the ADS conjecture of alpha bigger than equal to half, which is basically this, is just a tower version of the refined de Sitter conjecture, slightly modified here. So this is one connection that's interesting. On the other hand, in de Sitter space, you find precisely the opposite. Alpha must be less than or equal to a half. And the reason is that if the tower of states contains a massive spin-2 field, which any Kaluta-Klein tower will because they're Kaluta-Klein gravitons, but let's say in general if it contains a massive spin-2 field, then it's known that a massive spin-2 or higher field cannot have a mass that's less than the cosmological constant to the half. This is so-called Higuchi bound. You must satisfy this, and therefore it must be that in de Sitter space you find the opposite thing, that alpha is less than or equal to a half. So just take 1 or 2 minutes and then I'll finish. So let me just give about some evidence of these conjectures from string theory examples. So there's no known 10 or 11D counterexamples as far as we know, and there are many infinite sets of examples. No separation of scales is known to hold in supergravity. In other words, there's a kind of Maldacena Nunes for no separation of scales. So you require at least some orientifolds, and I think more precisely, as was argued here, you require scalar gradients from orientifolds. And it's known that scalar gradients cannot be supported on a coset manifold, and typically coset structures on this space are used to have a consistent truncation of finite number of fields, and so it's natural to suggest that any situation where we have a consistent truncation to finite number of fields will not have separation of scales, and in fact this was conjectured all the way back in 2007 to be true. Evidence against the conjecture, it is violated, the strong version at least, is violated in type theory and Calabi-Yauchow pactifications, although those are not 10-dimensional solutions. It should be validated generally by some kind of smeared source approximations, so it would be good to understand what that really means. Both conjectures are violated by KKLT, although they may be implicitly satisfied by some light towers of states that are related to complex structure moduli rather than scalar ones, and there are some other counterexample proposals. Let me just quickly discuss some relation to other ideas. There is a CFT dual interpretation of these statements, which is that there is no parametric gap between a dimension of a finite and an infinite number of operators. And I should mention that there was a paper actually that came out at the same time, which suggested also some kind of strong version of our conjecture, but said it's related to the presence of gauge symmetries rather than supersymmetry. So this is also an interesting possibility. And there is a relation to DS vacua. In particular, it suggests that it cannot have an effective theory that has a family of vacua that interpolate between ADS, Minkowski, and de Sitter. So if you have a family of vacua, as soon as you go up to the Minkowski limit, you must get an infinite tower of light states, and your effective theory breaks down. So you should not have a single theory interpolating between ADS and DS, like you get, for example, in uplift in KKLT. So this is something interesting to think about. And it also suggests that if our universe is de Sitter, if it really is a de Sitter space, then you should get a light tower of states. So I'll finish here because I'm a little bit over time. That's the conclusions. Thank you.
I'm sure there are questions, so who wants to ask? Arthur.
Is it on? Oh, okay. Can you hear me?
Yeah. Yes, very well.
So I have a feeling that if I take all these conjectures together, it appears that you are somehow in spirit at least saying that there cannot be an effective 4D field theory out of string theory, except n equals 2 Zuzi Minkowski.
So not about, so you cannot, so it's true, if you take the strong conjecture to be the case, if you look at a supersymmetric vacuum, then you cannot have an effective theory about a vacuum, so really a minimum, a supersymmetric vacuum of ADS, it's not four-dimensional indeed as you say, and the de Sitter one...
Sorry, I think I didn't... My statement is different. My question is different. Look, you're excluding de Sitter effective field theories anyway, right?
De Sitter?
De Sitter, you have excluded.
Yes.
You're now excluding effective theories which are truly ADS4, right?
Yes.
You cannot get Minkowski without n equals 2 Zuzi.
I
that
agree.
we know. Okay.
Yeah.
So as a sum of this, you are ruling out 4D quantum field theory.
No, because, yeah, as an expansion about a vacuum, that's true. But as you know, our universe could be not in a vacuum state. It could be in a rolling state. And then, of course, if it's slowly rolling, you can still define an effective field theory about that. We know that's perfectly fine. It's completely consistent with observations. So this will be fine. Our universe is perfectly compatible in principle with these things. But what you say is true. We're saying that you cannot have a vacuum about which you define a 4D effective theory. Yeah.
Okay, another question?
So here you're saying that as you send this cosmological constant to 0, you get a tower of light states. But so can you also like use this backwards if you say that all the infinite distance points will lead to cosmological constant becoming vanishing? Is that something you can say, or is that?
Yeah, I just in my first slide I mentioned this. This is a kind of correlation that you have, but it's not necessarily a causal connection. There's certainly at infinite distance, like decompatrification limits and things like that. Okay, you're asking maybe other infinite distances, not decompatrification limits.
Yeah.
Whether the cosmological constant has to go to 0 at infinite distance generally. Yeah, it could be. I've not really thought about it. I would guess yes. Yeah.
Thanks.
So can I also ask, so your first thing about lambda, so can I regard this as equivalent to a statement that the anthropic principle is kind of false as a principle, because that has its basis the idea that lambda is a flat prior, whereas so is that a fair summary that you're?
No, I wouldn't agree with that. No, because I would say the landscape anthropic argument would still hold perfectly fine, because you can just say that anthropically you have a very flat potential, which is rolling very flatly, like in quintessence kind of scenario, and indeed. Quintessence models are notoriously difficult from a naturalness perspective, so it's very natural to use a kind of anthropic argument for it.
So can I push you on, because the original kind of thing of Weinberg's approach to this was based on the idea that the lambda the zero you can regard as roughly a kind of flat prior, so that when you have constructions that there isn't anything particularly special about lambda is zero. So the idea that you can have just a random cancellation to get lambda equals zero, but nothing particularly special is happening at lambda equals zero. It would seem these statements would be...
Oh, you mean by signaling out lambda equals zero as special?
Yeah.
Then it changes the prior on the probability distribution of lambda? That's what you mean? Oh.
Yeah, the thing is that having lots of cancellations of terms to give you lambda is zero, that there's nothing special happening at lambda is zero. It seems that everything you're saying would be in
yeah, I don't know if that's the key point of the Weinberg argument, or I thought the main idea is that there's an upper bound on how big lambda could be anthropically from galaxy formation, and of course that's true equally for a slowly rolling scalar field. I mean, I don't see anything in, so yeah, I don't see why necessarily, but we can discuss it more later, yeah.
Yes, Elias.
What you were saying are applicable in critical string theory. Do you have any comment about sub or supercritical string theory?
Yeah, I mean, I think it's very interesting to think about supercritical string theory in particular, but I have no comment because I don't understand that theory well enough to, I don't know if anybody does understand it well enough to really have enough confidence. I guess my point is, if you want to understand counterexamples to these ideas, something like KKLT is much better understood than something like supercritical string theory. So I would say let's try and understand the best understood possible counterexamples first before going to things that I think are not so well understood, in my opinion anyway. But maybe you are more confident in our understanding of supercritical string theory, and then we can discuss that more.
Okay, one last question, if anyone has a question. If not, then let's thank Eran again for a nice talk.
Yes, one, two. To see. Yeah, okay, that's it. Okay. Okay, thanks a lot to the organizers for I skipped the introduction. For the invitation to come here. I will be discussing some issues of discrete properties or discrete structures in the landscape and in the Swampland. So this is work done in collaboration with several people, in particular my 4 very talented young students whose faces are here. So if you see them in the audience, you can ask them for more details. So the motivation for this work is, as all of you know, to navigate the Swampland and hopefully try to discover new structures. Let me take the opportunity to make some publicity, and I invite you to the workshop that we'll be having in Madrid next fall. And the ingredient, the structure that I'd like to discuss in the Swampland today is discreteness, basically, of typically field space, in particular action field space. And by discreteness, I mean things like periodicities of scalars, dualities in which different points in modular space are identified, monodromies, symmetries, and so on. So I will be focusing mostly on the Swampland distance conjecture that you have probably heard about many times in this workshop. But let me just
give a slogan for it and repeat it. Basically, it means that Transplanckian trips in field space are not allowed. But more precisely, let me put it in this way, and you can discuss about the precise terms, means that adiabatic motion in modular space over Transplanckian geodesic distances leads to some breakdown of effective field theory. And typically, as we heard in the previous talk, for instance, this means that if you go to some point close to infinity in field space or in modular space, you have the appearance of infinite towers of light modes. Typically, this happens in modular spaces, and you get these massless states as part of your effective theory, which then breaks down. In this respect, I'd like to discuss two particular points about this statement. The first one is whether you can have other disasters or other related disasters when you try to reach points at infinity in distance space, or what happens if you consider motions in field space which are not adiabatic, that is not just constant depths, but actually time-dependent or space-time dependent configurations of the different fields, which is kind of related to the previous talk as well. So I will be mostly focusing on actions, and that's where the discreteness will be coming in, because actions are, in a sense, just scalars with some periodic identification. They are very nice because they allow you to explore possibly super-Planckian regimes without achieving very high energies, if you wish. And that's because they are very strong symmetries that protect these actions. Basically, you have a perturbative symmetry, which is broken to discrete periodicities by, for instance, non-perturbative effects like instantons. And the typical picture that we may have in mind is to have situations where you have natural inflation, or it can be broken by some monodromic effects. And the typical picture that you may have in mind is the action monodromy. So let me just start with the first picture, which is the natural inflation one, which is, I mean, even if you don't have inflation in mind, it just means that you have some scalar with a perturbative exact global symmetry, which is broken by instantons. And the typical situation is to consider the first single instanton effect, which introduces this type of a cosine potential. And in the setup of inflation, this has been extensively discussed, especially after the 2014 BICEP announcement. Basically, in trying to achieve Transplanckian regimes, the first attempt was to consider the periodicity of the action to be very large, but typically if you try to do that top-down, basically you always find that you're at the edge of controllable regime, so you basically don't have a good understanding of your theory in that kind of situation. And in fact, it has been understood progressively that trying to achieve that, even with many actions and so on, is something which is in deep conflict with the Swampland conjectures, in particular with the weak gravity conjecture applied to actions. And this was already pointed out by Kundrum and collaborators in the original paper about weak gravity conjecture, and in multi-field cases and many other setups has been done, studied very systematically after 2014-15. Okay, so typical situation, what happens is that when you try to make your periodicity very large, typically there are towers of other effects which are coming in, which are other higher harmonics coming from higher instantons, which introduce further sources of the potential, which effectively reduce the periodicity in which you can travel. So even if the full periodicity is very large, your actually accessible field range is very small, or it is sub-Planckian. Okay. One thing that I would like to address in this respect is that, in a sense, periodicity of the actions is just one very simple example of duality. It corresponds to just sending t going to t plus 1 when you have a complexified action. So if you consider situations where you have a complexified actions, it's natural to think about other dualities, other identifications in modular space that kind of enhance your symmetry group, your identification group, from just t going to t plus 1 to also including situations like, or identifications of t going to minus 1 over t. That is the full SL2 set. So typically in many situations where you have the actions and this action, there are modular spaces which have these kind of modular spaces. And that means that your identifications in this field space are richer than just the action periodicity. And focusing on these kind of situations, you can try to do other things to achieve infinite distances. For instance, to go to infinite distance in this action field space. So, as I said at the very beginning, typically when you try to do that, and to go to infinity in this action direction, basically with coupling or very large volume and so on, typically you get this infinite tower of particles in your theory. But let me just make an extra twist that introduces a novel kind of disaster that I explored in this paper with Ibanez and Eduardo Gonzalo. Basically, Basically, the statement is that in many situations, these other fields which are becoming light, or degrees of freedom which are becoming light when you try to reach these infinite distances, induce scalar potentials that actually dynamically prevent you from reaching this point at infinity. So you cannot even get there. It's not that you get there and there are very light states, but you cannot even dynamically get there with a finite amount of energy. The key point is that because of these dualities, if you try to be the most general duality invariant scalar potential, typically it corresponds to some modular functions which have a very peculiar behavior at near the point at infinity, in which the scalar potential diverges. If you're familiar with all heterotic literature, basically this corresponds to the well-known fact that if you have compactifications of heterotic on K3 or orbitals, something like that, there are typically n equal to threshold corrections to gauge couplings. In n equal 1 vacua, you have those guys every time that you have some fixed torus in the orbifold. And this correction to the gauge couplings means that if you have gaugino condensations in some n equal 1 sector, there are very strong, in fact, the so-called poly-instanton corrections to your scalar potential, which reproduce this duality invariant modular function. So the type of potential that you get is a function like that diverges at the point at infinity in field space, so you cannot even get close to it with a finite amount of energy. So that's another kind of disaster that appears when you are kind of more careful about these identifications with the actions. The second situation that I would like to mention is what happens when you have action monodromy. The point is that the previous situation where you have this full duality group manifest in your theory is very unusual, and it's not that generic in the sense that every time you have some ingredient which is not invariant under the duality, for instance, if you have fluxes or things like that, you don't have that symmetry manifest in your theory, and actually the kind of setup that you have is a kind of action monodromy setup. And this can be already understood at the level of the periodicity of the action. Action monodromy means that basically what you have is some periodic action, but you have a periodic potential as well that respects this periodicity, but it's made out of an infinite number of branches, such that each branch alone is not periodic, but the whole set of branches is periodic. This has been studied again in the context of inflation for many years, and I will just recap a few features about it. Okay, so something which is nice about this action monodromy description is that if you dualize the scalar into a two-form, the appearance of the potential can be encapsulated, as was mentioned in the previous talk as well, in terms of a three-form with this kind of gauge invariance, in which the three-form is eating up the two-form dual to the action, and everybody is getting massive, and the massiveness of all these guys corresponds to the development appearance of this scalar potential. So dualizing back to scalars, basically you find that the key of the monodromy is this kind of topological coupling between scalars and field strengths of three forms, which was uncovered for different reasons by Valley and Kalop and Sorov as well. You can dualize this back by integrating the four form into just a mass term for this scalar or even more general potentials. So one important point about the discussion of whether one can use these action monodromy ideas to achieve Transplanckian distances is that as you start making your action very large, you are going up one of these branches, and then your energy is starting to go higher up, and you have to worry about how this back reacts on the whole compactification. And this is, has been some ongoing topic for several years, with typically the generic result that you cannot achieve Transplanckian distances. So let me just mention that it is true that you cannot achieve these Transplanckian distances adiabatically, but there is an issue about trying to do this adiabatically in the following sense. Adiabatic motion in field space basically means that if you have potentials, like in action monodromy, means that you're going off shell. That is, you're going up a slope, and then having a constant depth means that you're not satisfying the equations of motion. So in general, it's hard to try to address back reaction in this setup because you're sitting on the slope, and then the only solution to the equation of motion is to have something rolling or evolving dynamically. So it's hard to find those solutions and to study them. So in collaboration with the students, what we did is to consider one particular situation where you have a fully back-reacted 10D solution, which turns out to be a very familiar case, which is just one of these Klebanov-Strassler warp throats. So let me just remind you what these throats are. Basically, the starting point is to consider one of these holographic compactifications on anti-de Sitter 5s times T11, which is topologically S2 times S3, and then you have n units of Ramon-Ramon 5-form flux on the internal space. Let me explain that we're not having a separation of scales or whatever in this setup, but it doesn't matter so much for us for the moment. And the point is that there is a light scalar in this theory, we call it phi, which is coming from the NSNS2 form integrated over the 2 sphere. Okay? So we are thinking about this 5-dimensional theory whose vacuum is kind of anti-de Sitter. Now, we introduce some flux compactification in this theory. We introduce some extra flux, which is m units of Ramon-Ramon 3-form flux over the 3 sphere. And then the solution that Klebanov and Strassler proposed, based on earlier work by Klebanov and Seilin, is that the full solution is some kind of what we call locally anti-de Sitter 5 times S2 times S3. And we call it locally ADS5 because the cosmological constant is evolving in the radial direction. Basically, there is some H3 third-form flux in the, with one component in the radial direction, which is part of a non-compact space, if you wish, such that the scalar that we talked about before is rolling logarithmically with the radial coordinate. And because of the action monodromy in this picture, as we will mention later on, the 5-form flux is evolving also logarithmically and growing and changing as you move to larger and larger radii. And conversely, accordingly to that, there is some scalar potential, which when you minimize, basically tells you that the ADS5 radius is also evolving logarithmically with the radial direction. So in the language of the previous talk, as you go to larger distances, you're approaching infinite distance in field space, if you wish, because you're approaching some kind of the compactification limit. The difference perhaps is that in here you have one explicit scalar, which is an action, that it is rolling with the radial direction as you move in that direction. So you're not approaching that regime adiabatically, but with an actual space-time dependent rolling of one of the fields. Okay, and the full 10D supergravity is known. I didn't write it down, but it's in all the textbooks basically. So this example, this kind of warp throats that Klebanov and Strassler introduced for the conifold that exists for many other theories is a prototypical example of, let's say, action monodromy in 5 dimensions, in the sense that you can reinterpret the full solution as a model of action monodromy. The basic idea is that the 10-dimensional coupling of the Ramon-Ramon 3-form field strength, the NSNS 2-form field, and the Ramon-Ramon 5-form field strength reduce when you compactify on the 5 sphere because of the F3 flux, reduces to a coupling M5 F5, which is the 5-dimensional version of the Revali and Caloper-Sorbo coupling. So there is some action monodromy in which couples this 4-form and its 5-form field strength to this action. And basically, the potential for phi and the dynamics of phi follows from the potential that it's inherited because of this action monodromy structure. Okay, so because there is a potential for this action and you're going to larger and larger actions, there is a rolling effect which is there to solve the equations of motion. So we are properly accounting for the living on the slope in the sense of this theory, and properly accounting for solving the equations of motion. And all the dependencies of the cosmological constant and the flux on the radial distance just follow because they depend on the action because of the action monodromy structure. So in this kind of situation, you can measure what's the distance traveled by this action as you go to larger and larger r, and you find that you can that this scalar is rolling up to arbitrarily large distances in field space. And it's fine. I mean, this scalar can get transplanckian very easily. It can go to arbitrarily high distances. And the only reason why there is no conflict with the standard Swampland distance conjectures is that in here we're considering a non-adiabatic motion. That is, we are considering a situation where the scalar is not just a fixed bed, but actually is rolling dynamically. And this is very important for this solution to exist, solve the equations of motion, and also to escape the application of the hypothesis of the Swampland distance conjectures. Okay, so in the last few minutes, I wanted to move on to some slightly different topic, but which is related to these things, which is discrete symmetries in anti-de Sitter. Once you start studying scalars in anti-de Sitter, one of the things that you can do is this action monodromy, but another thing that you can do is to think about scalar actions with BF couplings or things like that, which basically are typically associated to Green-Schwarz mechanisms and to continuous U1 symmetries being broken to discrete subgroups. And that's one topic that we are trying to cover. And the point is that if you think about holography, there are infinite classes of n=1 gauge theories appearing from different range sitting at singularities, Calabi-Yau threefold singularities, which if they are toric, they are very easy to describe using a quiver diagram techniques and using dimer diagrams. Basically, these toric theories, they enjoy, in some circumstances, a lot of discrete global symmetries as field theories, and that means that in the holographic dual, in the gravity dual, there will be a lot of discrete gauge symmetries in this setup. So this kind of construction is a good arena to explore the role of discrete symmetries with the Swampland conjectures in a particular setup of anti-de Sitter, which is a nice endeavor, I think, because there is a lot of discussion about continuous gauge symmetries and continuous symmetries in the Swampland, but the situation for discrete symmetries is still, let's say, in the infancy. So basically what we are doing is we are using this dimer technology, these dimer diagrams, to build infinite classes of ADS compactifications in the holographic sense, that is, with no separation of scales or whatever, with arbitrarily large and very detailed, let's say, discrete gauge symmetries. So the kind of geometries that we are considering are like orbifolds of C3, orbifolds of coniform, orbifolds of the complex cone over dp1, you name it, many complicated situations, but which can be dealt with the combinatorics of dimers very easily. Okay, so something which is interesting is that generically you get non-abelian groups in the gravity dual, which are coming from torsion classes of the compactification space. So there are discrete symmetries which are not necessarily coming from the breaking of continuous symmetries, and that's something that may bring in some novel features for these theories, because not all of the properties of these discrete symmetries may be inherited from some continuous groups above. So let me just show you one of the pictures for these dimer diagrams, where we have a lot of different faces that correspond to the different gauge groups of the theory, and the edges correspond to the bifundamentals, and the nodes here correspond to the interaction terms in the superpotential, and we have labels on the edges which encode the charges under the discrete symmetries for all these theories. Okay, let me just move to the conclusions. So I discussed a few issues related to the interplay of discreteness and the Swampland, particular periodicities, dualities, monodromies, and symmetries. In a sense, my picture is that actions are just a particular case of scalars which have some discrete periodicities and global identification. So in that sense, it was important to think about other dualities as identifications in field space. And this brought about this new kind of disaster that may appear when you approach points at infinite distance in a field space. I discussed monodromies as periodicities in situations where you have not explicit dualities, but rather you have fluxes or torsion. And I discussed that it's important to include the back reaction and the non-adiabaticity, and that these kind of configurations, which are not usually considered in these Swampland discussions, is important, in particular because they really allow you to evade many of the Swampland criteria. And it may be useful in some applications. For instance, in inflation, there is actual rolling of the scalar in time, let's say. And finally, I discussed that these kind of monodromies or symmetries or identifications can become non-abelian in some cases, for instance, in this ADS toric quiver gauge theory dualities. So, thank you.
Questions? So, okay, thank you very much for a very nice talk. So, I have a question about your, the conclusion about this coming from this Kleber-Strasser analysis of the Kleber-Strasser axiom. So, in that model, also in many ADS-5 constantly models, you know from the beginning that your ADS-5 theory can be at most be interpreted as a consistent truncation, not really as an effective field theory.
Yes.
So how can you apply? I mean, I would say that if you find this Transplanckian excursion, okay, maybe it's interesting, maybe you can draw something, but does not immediately apply to Swampland conjecture for the ADS-phi effective field theories.
Sorry, can you repeat the question? The last part.
So since your ADS-phi theory cannot be, it just can be at most be regarded as a consistent truncation.
Yes.
So it's not really an effective field theory.
Mm-hmm.
So how can you use the result to?
Yeah, well, I would say that in this case it happened that there was a consistent truncation, but it's not the key point in the discussion, because you can build a very similar discussion with other throws where the compactification space is much less symmetric and you don't have any consistent truncation in that setup.
No, okay, but typically you have in these holographic models, you have a problem. I mean, you have no hierarchy between the Kaluza
Are you thinking
modes.
about the separation of scales?
Yes, no
I
separation
see.
of
Yeah.
scales. So from the beginning it was well known, no, this Kaluza invasion of the 80s for all these DS something.
Let me put it this way. I'm not putting emphasis on having some consistent compactification to ADS-5. I'm just thinking about the situation where I have some field which can travel in Transplanckian distance. So I can put it in the generalized framework of the previous talk by Eran, where I have some field, which you can think is a kind of living in 10 dimensions that can reach this Transplanckian regime, let's say, thanks to this particular dependence.
Okay, next, Cameron.
Yes, so just, I think, amplifying what he said already in his talk, I think it's crucial that he's violating adiabaticity in all these. So a lot of these things are, when you have a quasi-static position, that's where you talk about distance conjecture. So in particular in applications to inflation or other things, people want to have an adiabatic situation, not violating it. So his examples violate adiabaticity. But it's a much simpler example which shows that the issue is not separation of scales. For example, take elliptic fibration of K3. Take T2, as tau goes to infinity, you have a distance conjecture. But you easily know that if you take the elliptic fibration of K2, view that T2 fibered over P1, you can make T2 to be small and P1 to be big, and you move over regions where tau is infinite 24 times. And there's no light space. That's because you're violating adiabaticity at 24 points. So there's no, I mean, this is a much simpler example than the one he's talking about. It's a well-known one. You just take an example of K3 viewed as elliptic fibration. You're going through the infinite points 24 times with no massive space. That's well-known, of course. So the main point is that the distance conjecture applies to quasi-static situation or very mild movements, not violating adiabaticity.
Yeah.
That's one comment. The other thing I wanted to mention is that, of course, he mentioned it in his talk. I'm just trying to clarify. The example about the discrete symmetries being large in ADS, I think relates to Eran's talk, I think, in some way, that you won't be able to get infinitely large discrete groups if you include the extra space. In other words, there would be, in the full space, you don't have that discrete symmetry. Only in sub-loci you have it. So it's, again, the statement that you cannot separate ADS from the internal space. Otherwise, so to view the Swampland conjecture in the context of ADS, you always have to include this extra space. Otherwise, you get states which look very different from the rest of the Swampland.
Yeah, I'm fine with that. It's not that we're trying to make internal spaces more by quotienting and...
It would be good to phrase it in such a way that the Swampland picture looks the same for regardless of the space.
Yeah.
And so therefore, in that context, ADS should not be viewed as in isolation. The internal part is important.
Yeah.
Eran?
Thank you for the talk. The scalar field has a profile which is logarithmic in R. Phi goes at log R. And then if I look at the energy density in the kinetic terms of the scalar field, that's a derivative of it. So it goes like parallel in R. And then if I write the energy density in the kinetic term in terms of the field, it's exponential in the field. So when you go large variations, you get exponentially large energy densities from the gradient, from the kinetic term. So what I want to understand is how can you control exponentially large energy densities?
So it's exponential in the field, you mean, no?
Sorry?
It's exponential in the field.
In the field, exactly. But you are saying you can go to very large, if you go to very large field expectation values, then that means you go to exponentially large energy densities. So somehow you have to control these exponentially large energy densities. So this is what, in fact, in the paper that I wrote with Daniel Clever, we used precisely this logarithmic behavior to argue for the distance conjecture because of this exponentially large energy densities from the kinetic terms. But I just wondered how you handle them.
But if you consider the 10D supergravity solution of Klebanov-Strasser, you don't find anything.
Yeah, so maybe it's related to the fact that there's a warping, which is exponential. So this is what I don't. I was trying to understand. But if you try to have effective field theory within a finite mass range, this exponential energy densities would be hard to control.
Okay, so I'm going to come on here because I've got a relevant question on this, because this looks very similar to kind of cosmological behavior. Because if you have an ordinary kind of runaway potential, and you do the cosmological solution of that of a scalar field on a runaway potential, such as you get in every string king application, I mean that behaves as the field range goes as phi goes as log t, it goes as log of time, and what you have is it's the cosmological evolution of a scalar field, running down a runaway potential to infinity. So if it's a potential for the volume, you clearly move, Planck, you move infinite distances in field spaces. So to me, this looks very, very like a spatial version of a kind of the cosmological evolution.
The smallest idea.
Of a runaway field.
Yes.
Yeah.
Yes. So concerning your question, what I think this may be an objection towards the statement that you have a completely consistent 5-dimensional effective theory. And I'd say that there is even a stronger abstraction to that because there is no separation of scales in essence. Okay? So I would like to address the question of separation of scales, which may be impossible to solve before addressing the question of whether this effective theory in 5D makes sense all the way through. If you focus on the 10D solution, it's well defined for arbitrary large distances, and it's fine, and you don't see any problem associated to these exponential energy densities.
I just think the 10D solution is defined over infinite energy ranges. That's why if you write down an effective field with a finite cutoff, then you'll find these exponential energy densities. Okay, but we can discuss it later.
Okay.
Any last brief questions? Okay, let's